Hi guys. So far we've been studying differential calculus. That's the instantaneous rates of change, the slopes of tangent lines, and derivatives. Okay, but way back when they needed a method to describe how those instantaneous changes accumulate over an interval of time to produce another function. And this leads to what's called integral calculus. The challenge at the time for Newton and Leibniz, because they both did it separately at the same time, was to prove the connection between differential and integral calculus. And that's the fundamental theorem of calculus, which we will learn, but not yet. We're not quite ready for the fundamental theorem of calculus yet. But this discovery of the fundamental theorem of calculus became the single most powerful insight mathematicians have ever acquired for understanding how the universe works. Think of the power of that statement and how powerful that fundamental theorem of calculus is. And that is where we're headed. So we're going to start very simply. We're going to consider a car traveling 75 miles per hour from 7 a.m. to 9 a.m. And we want to know the total distance the car traveled. Well, we know that distance is velocity times time. And even if you forgot that, we know that the car is traveling 75 miles per hour. And our distance is in miles. So what do we have to do? We have to multiply by hours to get only miles. So we're driving 75 miles an hour from 7 to 9 a.m. That's for a total of 2 hours. So 75 times 2, that's 150 miles that the car has driven. Now, if we look at this graphically, here's the velocity at 75 miles per hour here, and it's 7 a.m. to 9 a.m. So if we look from 7 a.m. to 9 a.m., this shape here is a rectangle, right? And this is the curve, the velocity function. And if we look at this rectangle, the height of this rectangle is 75. And the base of this rectangle is 9 minus 7, which is 2. That 2 times 75 is the area under the curve. So that 150 miles came from finding the area under the function between the function and the x-axis. Now the problem is, this only occurs if you're driving with cruise control, and certainly not on Long Island. We never drive, you can't drive 75 miles per hour for 2 hours. Even if you are on cruise control, it's not going to happen. So it's more likely we're going to be driving like this. How do you find the area of that? And that was the problem they were trying to figure out. Okay, so what we're going to do is we're going to use what we call rectangular approximations, and that's what we're going to try first. But let's make sure we have some vocabulary straight. So we're going to use the function f of x equals x squared plus 3, and we're only going to look from x equals 0 to x equals 4. So this is 0, 1, 2, 3, and 4. Now, p would be if I decide to break this area up at 0, 1, 2, 3, and 4. This would be called a partition of the interval from 0 to 1, and each part is called a subinterval. Okay, so what we're doing is we're breaking it up from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And now we have 4 subintervals. Now the change in x from 0 to 1, we changed by 1. From 1 to 2, we changed by 1. From 2 to 3, we changed by 1. From 3 to 4, we changed by 1. So it's very consistent in this one. The delta x is always 1. The change in our x's is always 1. Now note, the width delta x does not always have to be 1, nor does the width always have to be the same for each one. That'll come later. So also each width may not be equal. But we are going to start with equal widths. We'll keep it simple to begin with. Now, how do we go about doing this? Well, there's several methods. The first one is abbreviated LRAM. That stands for Left Rectangular Approximation Method. Okay, now in LRAM, in order to do this, we use the left point of the subinterval to find the height of the rectangle. Now keep in mind that this height is the function value. So now here's the same graph of f of x is x squared plus 3. So this is the function. And we want to use 4 left triangles. So we're going to have n equals 4. That n is for the number of rectangles we want. So we're doing an LRAM sub 4. That means 4 rectangles. Well, let's look at the graph. We have from 0, 1, 2, 3, 4. Now between 0 and 1, the number on the left is 0. So we use the 0 to find the height of the curve. And then we follow that across to the end of the subinterval and finish our rectangle. Now between 1 and 2, 1 is on the left, so we use 1 to find the height of the rectangle and bring that over to the end of the interval, which is at 2. From 2 to 3, 2 is on the left, so we use the 2 to find the height of the rectangle and bring it over the length of the interval. Bring it down at 3. And from 3 to 4, the number on the left is the 3, so we're going to use 3 to find the height of our rectangle here. And we're going to bring it over the length of the interval. And now we have drawn our rectangular approximation. So we have drawn our left rectangular approximation. Now, what is that in actuality? This first rectangle, now notice the change in x is 1 on all of these, so the base is 1. Now, how do you find the area of a rectangle? It's just base times height. So the base is 1, and the height of the first rectangle, we use the function value at 0, plus the second rectangle, the base is still 1, and we used the 1 to find the height of the function. Plus on the next rectangle, the base is 1, and we used the 2 to find the height of the rectangle. And the next one, the base is 1, and we used the 3 to find the height of the rectangle. Now notice 1 times anything is just the anything, so I don't have to keep writing the 1 times. But f of 0, now remember our function is going to tell us that it's 0 squared plus 3. Now f of 1, 1 squared is 1 plus 3. 2 squared is 4 plus 3. And 3 squared is 9 plus 3. So this is going to give us 3 plus 4 plus 7 plus 12. This is 10, 22, 26 is our approximation for this area. Now, is this a great approximation? You can see all of this area we didn't count, and all of this area above the rectangle but below the curve that we didn't count, and all of this area, and all of this area. So this is an underestimate of the actual area. This time it's an underestimate. Does not mean it will always be. We'll talk about when it will and when it won't a little later. One thing at a time. Let's try the next method. The next method is an RRAM. That's a right rectangular approximation method. And for the RRAM, we're going to use the right point of each subinterval to find the height of the rectangle. And again, the height is the function value. So again, we're using the same function x squared plus 3, and we want 4 right triangles. So we're going to use n equals 4. So again, we're going to go from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And we're going to do an RRAM sub 4 because we have 4 rectangles. So the first rectangle, if we look between 0 and 1, 1 is on the right, so we use that to find the height. Then we go back to the start of the interval and down to 0. So think about what we just did. The base is 1, and we use the right endpoint 1 to find the height. Plus, now between 1 and 2, 2 is the number on the right, so we use 2 to find the height. Follow it back to the beginning of the interval and down. Now we have that rectangle. The base of that rectangle is 1. From 1 to 2 is a change of 1. And the height, we're using 2 to find the height of the function. Now let's do our third rectangle. So from 2 to 3, 3 is on the right. So we're going to use the 3 to find the height of the rectangle. Follow it back to the beginning of the interval. And then down to where x is 2. So the base of that rectangle from 2 to 3 is 1. And then in the function, we're going to use the right endpoint 3. And the last interval from 3 to 4, 4 is on the right end, so we use 4 to find the height. Follow it back to the beginning of that interval and down to 3. That change from 3 to 4 is 1, so the base is 1, and we're going to use 4 in the function to find the height of the rectangle. Awesome. So again, 1 times anything is the anything, so I don't need to worry about it. We're plugging these numbers into the function x squared plus 3. So that's going to be 1 squared is 1 plus 3, and then 2 squared is 4 plus 3, and then 3 squared is 9 plus 3, and then 4 squared is 16 plus 3. So we have 4 plus 7 plus 12 plus 19. And if we add this up, this is 11, this is 23, and we'll get 42 altogether. Notice that area is much larger than the left rectangular approximation. But you'll also notice all this area in this rectangle is above the curve. Here too, this area is above the curve. And so is this, and so is this. This is an overestimate. And again, an RRAM will not always be an overestimate. Okay, but this time it is. Now, how can we get a better approximation? Before we had the first one, we had a lot under, it was an underestimate, then we had a lot over, it was over an estimate. Can we get a little closer? Well, there's something called an MRAM. This is our third method. Now, an MRAM, can you guess? That's a midpoint rectangular approximation method. Now, for the midpoint rectangular approximation, we're going to use the midpoint of each subinterval to find the height of the rectangle. And again, we're going to use the same function, and we're still using 4, right? Oh, midpoint rectangles. And we're using 4 midpoint rectangles. That should say midpoint, not right. Sorry. So we're going to do an MRAM sub 4. Now from 0 to 1, 1/2 is in the middle. Now it's still a change of 1. The delta x is still going from 0 to 1, so the base is still 1, but we're going to use the height at 1/2 to find the height of the curve. And we go the left and right to get to the endpoints and then down. So what did we do? We used a change in the base as 1, and we used 1/2 to find the height of the rectangle. Now between 1 and 2, halfway between that is 1.5 or 3/2. But notice the delta x, or the base, or the width, is still 1. So it's still 1 times, but we're going to use 3/2 to find the height this time. And I go to the left endpoint, I go to the right endpoint, I come down on each side, I have my rectangle. Now the next subinterval goes from 2 to 3, and halfway between it is 5/2, or 2.5. But again, the base is still 1. So it's 1 times f of 5/2. And I'm going to follow there. Left, little to the right, down and down. And we have one more subinterval from 3 to 4. The delta x is still 1, but halfway between that is 7/2. So we're going to have a base of 1, and the height is f of 7/2. Now I'm going to go straight up. I'm going to go to the right and the left. It's a little slanty, sorry. All the way down. All the way down. And now we just have, so we have the picture, and now we have some computations to do. So now we're going to have 1/2 squared is 1/4 plus 3, plus 3/2 is 9/4 plus 3, plus f of 5 is 25/4 plus 3, plus f of 7/2 is 49/4 plus 3. Now if I just add up my 3's, 3, 6, 9, 12. That's 12. Okay. Now let's add up here. 1 and 49 is 50, 75, 84 fourths. Now 4 goes into 84 21 times, whoops, which means we have a sum of 33. And notice that 33 is between the LRAM of 26 and the RRAM of 42. It is not always going to be a perfect average, but it is going to be somewhere in between there. And notice we have some area that we didn't measure, but some that we did. Some that we didn't, some that's too much. Some that we didn't, some that's too much. Some that we didn't, some that's too much. A little bit on both sides, but it is definitely a closer approximation. What's another way we could get a better approximation? That would be to use more rectangles. So suppose we use the same function, but this time we use 8 left rectangles. So now we're going to let n be 8. So we're doing an LRAM sub 8. Okay, so we're still going. Now I want to look at this delta x here. This time we're going 0, 1, 2, 3, 4. That only gives us 4 subintervals. We have to cut each of those in half so that we can have 8. 1 half, 3 halves, 5 halves, and 7 halves. So this time delta x is 1 half. So now let's look at the first rectangle. The base is 1 half. And we're doing an LRAM, so between 0 and 1 half, that's our first subinterval. Which one's on the left? That would be 0. So we're going to use the height at 0, and we're going to come over about halfway and come straight down. There we go. Now the next one, between 1 half and 1, that's a change or a base of 1 half, and which one's on the left? That would be 1 half. So we're going to use 1 half to find the height. So from 1 half, we go up to the curve, come across to 1, and down. All right, next rectangle, from 1 to 3 halves. That's a change of 1 half. Which one's on the left? The 1 is on the left, so we're going to use the height at 1. We're going to come across to the middle, and we're going to come down to 1 half. The next subinterval, from 3 halves to 2, has a base of 1 half, and 3 halves is on the left. So we are going to use the height at 3 halves, and then we're going to come across to the end of the subinterval and come down. Now we have an interval from 2 to 5. Again, that's a change of 1 half, but 2 is on the left, so we're going to use the height at 2. We're going to go up, then we're going to come over, then we're going to come down. Next, from 5 halves to 3, that's also a change of 1 half, but 5 halves is on the left. We're going to use the height at 5 halves. We're going to come over to the end of the subinterval, and we're going to come down at 3. Now from 3 to 7 halves, that's a base of 1 half, and 3 is on the left. So we're going to use the height at 3. We're going to come over halfway. We're going to come down. Then from 7 halves to 4, that's also a change of 1 half, and 7 halves is on the left, so we're doing f of 7 halves. Now we have to draw that in, so from 7 halves straight up to the curve, over to the 4, and down. So you can see that, yes, there's still an underestimate, but it's much less of an underestimate, okay? Now, notice we have a 1 half in each part here. We can factor out that common 1 half. So we're going to factor out a 1 half. And now we're going to find f of 0, which is 0 plus 3. F of 1 half is 1/4 plus 3. F of 1 is 1 plus 3. F of 3 halves is 9/4 plus 3. F of 2 is 4 plus 3. F of 5 halves is 25/4 plus 3. F of 3 is 9 plus 3. And f of 7 halves is 49/4 plus 3. So we still have 1 half times. Now, if we add up our 3's. 3, 6, 9, 12, 15, 18, 21, that's 24. We also have some other integers here. We have a 1 and 4 and 9. So that's going to be 14. And then if we look at our fractions, we're going to have 1/4 plus 9/4 plus 25/4 plus 49, 50, 75. We're going to have 84/4 again. So now we have 1/2 times 38 plus 84/4 was 21. So that's 1/2 times 59, which is 59 halves, or 29.5. But you can see that that has gotten closer to the answer that we want. It was bigger than the 26, but it's still smaller than the MRAM. Okay, one more problem that's not a graph. So here's a numerical problem. The National Weather Service kept track of the rate of snowfall for our most recent snowstorm. The snowstorm started at 9 a.m., which we will represent at 0. So this is 9 a.m. The rate of snowfall was recorded every hour from 9 a.m. to 3 p.m. in centimeters per hour. Estimate the amount of snowfall. So notice each hour from 0 to 1 is 1, 1 to 2 is 1, 2 to 3 is 1, 3 to 4 is 1, 4 to 5 is 1, 5 to 6 is 1. That change in the time is 1 every single time. That's nice to know. In a table, that's usually where they're going to make the number different. The change in t is different, so look for it. So we're going to estimate the amount of snowfall, because if you think the snowfall is centimeters over hours, and if we multiply that by the number of hours, that'll give us the centimeters of snowfall. So we're going to estimate the amount of snowfall by using 3 left rectangles. So we're going to do an LRAM sub 3. So we're not going to draw it, we're just going to do it. So if we think about this, from 0 to 6, so let's think about our delta t. We're going from 6 to 0, and we want 3 subintervals. 6 divided by 3 is 2. So we're going to go from 0 to 2, 2 to 4, and 4 to 6. That's what we're going to use. So we're actually going to use a delta t of 2. So we're going to have an LRAM. Our change is 2, but between 0 and 2, 0 is on the left-hand side. Plus, from 2 to 4, the delta t was 4, but between 2 and 4, 2 is on the left. And then from 4 to 6, the change in t from 4 to 6 is 2, but 4 is on the left, so we do f of 4. Now you can factor out the 2, or you can leave the 2 there. It's totally up to you. F of 0 on the table is 1, plus 2 times f of 2 is 1.4, plus 2 times f of 4 is 0.75. So that's going to give me 2 plus 2.8 plus 1.5. That's 6.3 centimeters. Nice. Okay, there we go. Now, let's estimate this time by using 3 right rectangles. So again, we're going to use 3. So we're going to have delta t is going to be the length of the interval, and we're going to divide it by, we want 3 rectangles. So that's going to give us a 2 again. So from 0 to 2, 2 to 4, 4 to 6. So our right RAM, sub 3, our delta t is 2. So the base is 2, but from 0 to 2, 2 is on the right, so we're going to use f of 2 to find the height. From 2 to 4, the change in t, or the base, is 2, but 4 is on the right, so we're going to use f of 4 to find the height of the rectangle. From 4 to 6, the change in the x's is 2, and 6 is on the right, so we're going to use that. So we're going to have 2 times f of 2 is 1.4, plus 2 times f of 4 is 0.75, plus 2 times f of 6 is 0.25. So that's going to give us 2.8 plus 1.5 plus 0.5, so that's 2. That's going to give us 4.8 centimeters. Yay! One more part. So now we're going to estimate the amount of snowfall by using 3 midpoint rectangles. So again, we're still using 3, which means our delta t is still 2. However, we're doing an MRAM, which means we're going to use the 1 to find the height, the 3 to find the height, and the 5 to find the height. Okay, so our MRAM sub 3 is going to be our delta t. Our delta t is 2 times f of, in the middle of 0 and 2 is 1, plus then our delta t is 2 from 2 to 4, and 3 is the midpoint, so we do f of 3, plus from 4 to 6, the base is 2, and the midpoint of 4 and 6 is 5. So we're going to have 2 times f of 1 is 1.3, plus 2 times f of 3 is 1.5, plus 2 times f of 5 is 0.5. So this is going to give us 2.6 plus 3 plus 1, so that's 6.6 centimeters. All right, guys, so we learned a lot today. We learned that we're starting integral calculus. We're learning how to approximate area underneath a curve. We've done left rectangular approximations, right rectangular approximations, midpoint rectangular approximations, and we learned that if we use more rectangles, we have a better approximation. All right, guys, have a great day.